What's I go to? I see.
Good night, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open session 58 of the seminar. Today we have the excellent speaker, Roberto Triggiani. Introducing Roberto Triggiani, we have the Professor Lauren Prove. Thank you, Lauren. You can start.
Thank you, Juan. Well, good evening for everyone. It's a huge pleasure to introduce Professor Roberto Triggiani today. He's a distinguished university professor at the University of Memphis, and he is also an emeritus professor at the University of Virginia. He has more than 12,000 citations, and he has also an H-index 58. His area of expertise in partial differential equations covered topics related with optimal control, inverse problems, and control theory. And his talk is entitled Uniform Stabilization of the Boussinesq System in Besov Spaces of Low Regularity by a Localized Finite Dimensional Per Boundary Interior of Feedback Controllers. So, Professor Triggiani, you can start.
Thank you very much for the invitation, and thank you again. My apologies for postponing because of circumstances out of my control. So the topic that I've shown today is in the area of control theory of partial differential equation. In particular, the focus is on the stabilization problem. What is the Boussinesq system? The Boussinesq system, as you will see in a moment, is a system that couples the Navier-Stokes equation with the thermal equation, with the coupling which is due to the to the modeling of the physical modeling. And I will explain in a second in my next transparency why Besov spaces with the low regularity. Why the stabilization will be in the uniform topology of these Besov spaces, which I will indicate as we go along. And the main thing here is that I will do a stabilization. There will be, in fact, two parts. The first part, the feedback controllers are localized, are finite dimensional, and in the first part there will be interior. So interior localized means with the support arbitrary small. Interior means interior for the fluid, the Navier-Stokes, interior for the thermal. But then the second part will be boundary interior. Will be the control will be localized on the boundary for the thermal equation and interior for the Navier-Stokes equation. What we are the next topic in this direction will be boundary. This will be done in the next few months. Okay, so first of all, why a suitable Besov spaces setting of low regularity, and particularly this in the dimension d equal 3. The emphasis would be on dimension d equal 3, and the reason is the following: the Boussinesq system, as we will see in a moment, couples the Navier-Stokes equation with the thermal equation in order to model viscous, incompressible, heat-conducting fluid. Now, in the case of the three-dimensional Navier-Stokes equation, a suitable Besov space of low regularity, which in dimension 3 is close to L3, was instrumental to solve the uniform stabilization problem near an unstable equilibrium solution by means of feedback controllers which are localized, so with the support arbitrary small, on the boundary based, static, not dynamic, static, and also tangential on the boundary. And the open problem was for 20 years, they're finite dimensional. And in order to get finite dimensionality, I will explain this in a moment, it was necessary to abandon the sublet space theory, which is traditional in all this stabilization problem for parabolic type of dynamics, and move into the Besov space. And I will explain later on why. The solution to this, this was, the stabilization of Navier-Stokes equation started essentially around 2000 by Andrei Fursikov in Moscow. And the problem that was open for a long time was in three-dimensional, the uniform stabilization by feedback controller, which are finite dimensional. And this is a very long paper that has been published in Archive of Rational Mechanics and Analysis. This will be transformed into a book in the next few months. The original submission was 30 pages longer than it is. Eventually, there are what, 80 pages or so, and the book will be, or will be in the London lecture notes of the Cambridge University publication team. Okay, now I'm losing. Okay, in the case of dimension 2, the solution in a Sobolev space in the Hilbert setting h1/2 minus epsilon was done in my paper with Irena Leszewska in nonlinear analysis in 2015, and in the same reference, the dimension d equal 3 is also studied in the natural space, which now is h1/2 plus epsilon, but required an assumption. The assumption required was the initial condition be compactly supported. And it was in order to eliminate this assumption that was necessary, in fact, instrumental, to abandon the the Sobolev setting and move into a Besov setting. Why? The reason is that in dimension 3, the space has to be h1/2 plus epsilon, and as such recognizes compatibility condition. And that exactly the compatibility condition that forced the approach was based on a Riccati equation, which is also traditional in this area. We have 2 books on this in this direction. And you know, in order to take advantage, in order to take care of the compatibility condition, it was necessary essentially to take initial conditions which were compactly supported. So the feedback stabilization was a sum of 2 terms, one which is finite dimensional, and the other which is infinite dimensional, which however becomes 0 if the initial data are become compactly supported. So the function space which was required for dimension d equal 3 had to accommodate 2 essentially conflicting features. On the one hand, it had to be topologically low enough in order not to recognize compatibility condition, and on the other hand, it had to be topologically high enough as to allow the handling of the 3D nonlinearity in the Navier-Stokes equation. And the Besov space introduced below, also, which was initially done for the Navier-Stokes equation, which is also repeated here for the Boussinesq system, with very tight indices, as I will clarify in a moment, satisfy these 2 conflicting requirements. Oh, no, I mean, wait a second. Yeah, I have to get it. So, selector literature on Boussinesq stabilization is the following. When we started a few years ago, there was a paper of 2003 about stabilization by 2 internal controllers, both infinite dimensional. So was adding and subtracting. And so this was instead, the presentation here follows a bunch of paper where there are, every time the feedback stabilization is by finite dimensional controllers, everything Besov setting. So there is, by the way, Boudica is our first PhD student at the University of Memphis. And you see the paper that I'm going to, the presentation of the second part of the presentation with the boundary, with 1 control on the boundary for the thermal equation is based on this paper in the Journal of Inverse and Nilpost problem. It's also based on Kahneman type of estimate, which appeared in 2002. And before doing that, before doing the boundary, one of the control on the boundary, we wanted to do interior just to test the technique. And this was done in this paper of discrete dynamical system, where you see here the both controllers and the interior. I will describe this in the first part of my talk here. Now, a critical thing in all parabolic problem is at the very, very beginning. If one does not solve the problem, the one really has to change job, because it's at the level of testing the Kalman rank condition for a finite dimensional unstable problem, which I will describe, but it's not a matrix theory problem, it's a PDE problem. So some property about the traces or the restriction of the eigenfunction corresponding to an unstable eigenvalue. And so to do this, there is this paper here. Wang is a former student of PhD from the University of Virginia. You see, look, is unique continuation properties of static Boussinesq eigenproblem, which are overdetermined in a certain way, with application to uniform stabilization of dynamic Boussinesq system. And this is a paper which just appeared in Applied Mathematical Presentation. In fact, in my talk in Chapman University 10 days ago, I gave a talk exactly on this problem for 45 minutes or whatever. In turn, this for the Boussinesq relies, and is based on Kahneman estimate, and relies on this paper of mine on the unique continuation for arbitrary interior subdomain of the variable coefficient Gaussian equation, which is related, of course, is a linearized component of the Navier-Stokes equation. And both this paper use intrinsically Kahneman type of estimate, which we were doing in the early 2000 for controllability and stabilization of this type hyperbolic equation. Okay, now you reduce by looking at the elliptic operator, the Laplacian, and you take the component, the part of the Kahneman estimate corresponding to this operator. Okay, another component which is critical for the solution of this problem is given here, and it is again, there's Boudica, who is in Europe, by the way, is a postdoc, is about the maximal LP regularity for an abstract evolution equation with application to closed loop boundary feedback problem. Now, the maximal regularity is a topic that has been around for a long time. The first paper on maximal regularity was on a Hilbert space, and it goes back to 1965 in Italian, De Simone. And then it shows that analyticity and maximal regularity, so for analytic semigroup, maximal regularity and analyticity in the Hilbert space are the same, but not in the LP case, which is here, where you can have analyticity, but then you have to show if there exists maximal regularity. And this paper uses the so-called R-boundless theory. And the novelty is that the whole literature, which was mostly actually in Europe, Germany and Italy, the literature consider various parabolic problems, but with homogeneous boundary condition typically. Here instead, we want closed loop boundary feedback problem. So it's a completely different thing. Okay, select the controllability references for this Boussinesq as given here. And now I can finally, in the second part of my presentation, I will do the boundary stabilization, where the thermal equation will have a control on an arbitrary small portion of the boundary, gamma tilde, and the Navier-Stokes equation will have a control in the interior and little omega, which is supported by gamma tilde. And that will be done, in the second part of the talk. So here it is. So this is a Boussinesq system, which is it models a viscous, incompressible heat conducting fluid. So what do we have? In boldface means there's a vector, three-dimensional, let's say, y. So this is the Navier-Stokes with the classical Navier-Stokes nonlinearity, and the pi is the pressure, and is coupled with the variable theta, which is given here, which in turn is the variable of the heat equation, or the diffusion equation, which in turn is coupled with y, according to this nonlinear term here. The ED is a very special vector, which I will describe in a second, and then F and G, as given here, are external force acting on the Navier-Stokes equation, and the G is the heat equation, the heat source density acting on the heat equation. So y, let's say three-dimensional, is the fluid velocity, theta is the scalar temperature, nu is usually the kinematic viscosity coefficient and the thermal coefficient. Very important thing is this vector ED here, which comes from the modeling. ED in three-dimensional is a one-dimensional z vector in the z direction, 0, 0, 1. And the thing with the G and G theta given here are really constant. So for instance, this one here is a reference temperature. So it is a Navier-Stokes coupled with the thermal equation. And at the beginning here, I take boundary condition to be 0 for both of them. Okay, So the starting point of our analysis is the following result. The theorem, we look at the steady state equation. So we eliminate the terms which depends on time. So this everything depends only on the space variable. So is this space variable or the static, if you like, part of the Navier-Stokes equation, which is sub B means equilibrium. So y equilibrium. Pi theta is the pressure, coupled with the theta sub B again for the thermal equation, which is given here. And in terms, this is coupled with OE. So this is coupled with y, and y is coupled with theta. And divergence free, of course, because of the Navier-Stokes. And then on the boundary, the two variables are zero. Now, the literature tells us that for q greater than 1 and less than infinity, for any data here, f and g in Q, then there exists a solution which generally is not unique, like in the case of the Navier-Stokes equation, which for y gains two derivatives, for theta also two derivatives, and then for pi is one derivative modulo constant. And notice that there are several references in the paper regarding q equal 2, but for q different from 2, see that the references are very recent. So this one is 2019. Okay, so the starting point of the stabilization problem is the following: that under a given external force F, a given heat source G of the thermal equation, given viscosity coefficient nu on the Navier-Stokes equation, and thermal conductivity in the thermal equation, we want to start from a bad situation. The bad situation being the equilibrium solution, which has been asserted by the previous result, is unstable in a qualitative sense, to be made more precise in the next transparency. What does it mean? We have to do with two parabolic problems. So we look at the linearized version of the parabolic problem, which will produce an operator which is here, capital A or script A, whatever it is, which will be defined below. And because they're both parabolic, the linearized, so the linearized version produces an analytic semigroup, parabolicity. In addition, being on the bounded domain has compact resolvent, the generator, and therefore the spectrum, which we want to assume to be unstable, it consists of, first of all, is inside the traditional, triangular sector, and instability means that there are n unstable eigenvalue because the spectrum is entirely point spectrum, which are on the right-hand side of the complex plane, lambda 1 up to lambda n. And m of them, m denotes how many are distinct, and lambda sub j is a geometric as opposed to algebraic multiplicity. In fact, everything is in terms of the geometric multiplicity, which is more difficult to do, by the way. So instability means there are the unstable eigenvalues on the right side of the complex plane. Okay, let me give you a quick review of historical perspective of the problem of stabilization for a parabolic problem. The boundary stabilization, feedback stabilization of a stable classical parabolic equation, let's say the heat equation of stable, just to give an idea, scalar, first linear and then defined on a general multidimensional domain, was intensively investigated in the period 73-83. And the general strategy was, in fact, in my PhD thesis in Minnesota in 73, which was published 2 years later, and is based on the following steps, which are important for all the parabolic problem. In fact, this technique has been used, in the literature consistently. For sake of illustration, I will write the PD problem in the linear case, because I want to start with the linear, obviously, in an abstract form, in an abstract space W. So it will be y sub t equal AW. A is the generator of a strongly continuous analytic semigroup with compact resolvent, like in our case. B, if we want to think about the control operator B coming from the boundary, then I don't want to get involved in the technicality, but it's a very bad unbounded operator, as if the control is acting on the boundary. And U, of course, is the control, it's the forcing term. The preliminary assumption, which was made for this classical parabolic, was the one I just described, that if u equals 0, so we look only at the generator A, denotes this generator has n unstable eigenvalues because it's a generator of analytic semigroup with compact resolvent. And then the technique was proposed is the following. Introduce a projection operator P sub n, which is defined in terms of the resolvent, with the curve C, which circles all the n unstable eigenvalues. So this defines a projection from the whole infinite dimensional space W into W sub U means unstable. And then you decompose the space into direct sum decomposition. So an unstable part, W sub U, which is a dimension n, essentially is the generalized eigenspace of the unstable eigenvalue. And then the W sub S stands for stable, which account for all the eigenvalues which are on the left-hand side. The analytic semigroup, the location of the spectrum determines the exponential decay. So you use this projection on the whole space, plus I minus the complement minus the projection, and you get the two subspaces, the W unstable, finite dimensional, and W stable. You apply the projection to the operator, so A sub super U will become the restriction of A on this finite dimensional unstable, and the same thing for A sub S. Okay, then step one, you want to split the linearized W dynamic into two components. A component W sub n, which is finite dimensional and by definition is unstable, which is part of the defined on this generalized eigenspace corresponding to the unstable eigenvalues. And then the companion part, the zeta sub n, which is infinite dimensional and defined on the stable part of the spectrum starting from lambda n plus 1 and going to infinity. So the finite dimensional component satisfied, if you apply Pn, satisfy this equation, which is finite dimensional with finite dimensional operator, A super U unstable, Pn applied to this operator control operator, let's call it B1, and the infinite dimensional is then here. But this is unstable. So the step two is we want to stabilize this finite dimensional unstable eigenspace component, which is defined by a pair of two finite dimensional operator. And we want to do this by state feedback, which is static, and which produces an arbitrary large decay rate. What does this mean? It means that we want to find, if possible, a feedback finite dimensional operator F, such that if the input U here is a feedback operator of the state, whereby the equation becomes just an equation in which U is being replaced by F W sub n, the new equation here is exponentially stable. We want to find an F, is possible, in such a way that with the pair AU and B1 given, the new problem in a feedback form become exponentially stable. Not only that, but with rho arbitrary large, but at least bigger than the absolute value of the first stable problem. And this picture here tells you exactly what's called feedback. So you have a system, you have the solution, you have a feedback up. It's like a thermostat applied to the solution, and you want to write an input, which is U, which is exactly F applied to W sub n. Now, in order to do this, in order to see whether or not you can find such an F, to obtain such a result, which some books like the one of Zabjic, for instance, called complete stabilization, one needs to verify the property of controllability. You go back now to 1970, when the people in control, mostly I have to say, in electrical engineering department, they were, they were very good in smart mathematically at the algebra level, and we want to satisfy the controllability of the Kalman algebraic condition, because this property, which in the literature sometimes is called pole allocation, so you can put the spectrum wherever you want with the feedback, is equivalent to the controllability property. Now, in the case in question, where we start from a PDE and we proceeded with this technique of projection of the infinite dimensional PDE, the question to say is that depending on whether the control action U is chosen to be located either a regional PDE, so perhaps an arbitrary small part of the interior, perhaps an arbitrary part of the boundary. This condition may well be false. I don't have time to give an example, but for instance, for the Navier-Stokes, if you do a certain thing with the boundary control on a small portion of the boundary, you cannot do that because this finite dimensional thing is false, and even in dimension equal to. And if it's true, it may be challenging to establish. In any case, this is not a metric step theory problem or finite dimension. It depends on the suitable overdetermined unique continuation property of the adjoint eigenproblem, the elliptic system, corresponding to the unstable eigenvalues of the adjoint problem. So this operator A unstable with a star, the adjoint. Okay, first part. So what we want to do, what is the qualitative goal? The qualitative goal is to introduce a control, possibly in feedback form, possibly finite dimensional, if we can make it, minimally invasive, that stabilize the Boussinesq system in the vicinity of an equilibrium, a stable equilibrium pair, which is Y equilibrium, theta equilibrium. And in fact, we want to do this in a uniform exponential decay with respect to the topology that we are working with. Let me start quickly with the preliminary case, which is when the feedback control are both interior but localized. So because before doing the most challenging thing with the boundary, you want to see the technique and what are the difficulty, etc., in a more in a less challenging problem, which is when both controls are on the boundary. So you take a little omega here, arbitrarily small, and then you look at the Boussinesq problem, particularly dimension 3, if you care, and you put a control U on the Navier-Stokes equation and a control V in the thermal equation, both interior, the same interior has to be, with M, which is the characteristic function. So is 1 on the omega and 0 elsewhere. And this is the paper that I was mentioning before. So now we have a control problem, the Boussinesq under control of U, interior control U and V, or an arbitrary portion of the interior. Okay. And okay, I already said that. Okay, so to establish this interior localized exponential stabilization near an unstable equilibrium solution, we want to do this by means of finite dimensional localized means arbitrary small support, feedback control pair. So M is the characteristic function, U is the control on the Navier-Stokes, and V is the control on the thermal, acting on the same interior subset. In the important case in which initial condition is of low regularity. In fact, technically expressed by the fact that the state space or the setting space or topological setting is this Besov space with tight indices that we described, which I'm going to describe in a moment. In particular, will be corresponding to LQ, where the Q is greater than the dimension of the problem. So the basic functional setting, which was introduced for the Navier-Stokes equation in the paper of the archive that I mentioned before, is the following. Let me start from here. This is a real interpolation space between LQ and W2Q with these indices. And you call this space, this Besov space, with this indices here, 2 minus 2 over P, etc., etc. And the P is to be trapped between 1 and 2Q minus 1, where Q is greater than the dimension. Suppose that the dimension is 3, so you get 6 here, 6 minus 1 is 5. So P is very tight between 1 and 6 over 5, as we will be said, clearly in the next transparency. Now, so this is a basic Besov space, but of this we take a suitable subspace, which I will define later on. So the tilde means a suitable subspace of this Besov space. And so what is the story here? That in order to, as in the case of the Navier-Stokes stabilization, the technical steps, which I mentioned at the beginning related to all this parabolic problem, is at the level of examining the controllability property of the finite dimensional projected unstable system. Now, as I mentioned before, this, as in the case of the Navier-Stokes equation, rests on the unique, and also parabolic problem, by the way, the classical parabolic problem, rests on a unique continuation property of the eigenfunctions of the eigenvalues which are unstable. Now, there is a big difference between the Navier-Stokes and the Boussinesq, and it is the following. Technically, it has been known now for many years, since the 70s and 80s. The controllability test of any projector system actually relates to this unique continuation property, not for the original system, but for the adjoint. But in the case of the Navier-Stokes, whether you look at this property for the Gaussian operator means the linearization of the Navier-Stokes, or the adjoint, it doesn't make any difference, they're equivalent. Instead, for the Boussinesq system, it makes a much colossal difference, because the adjoint is this linearized component, okay, of the linearized operator for the Boussinesq. What happens is that the coupling operator, because there are two equations which are coupled, the coupling operator, which I will mention later on, switch places. And because of the presence of the form of this the vector ED, which occurs in the system, in the model, which is 0,0,1, it turns out that the adjoint is more favorable, so it requires less condition. It's more desirable to look at the adjoint than to look at the original. So looking at the adjoint, you can get with less condition, which I will mention later on. So let me go quickly over this. So what you do, of course, being the Navier-Stokes, you decompose the space with the Helmholtz-Leray decomposition. So the space LQ is the direct sum of LQ sigma. Sigma stands for solenoidal vector space, and the complementary part, which is the gradient field, so which is given here. If for p equal 2 is orthogonal, but in general it is not. Essentially, this can always be done except for very special pathological omega, etc., etc. And what is LQ sigma? LQ sigma is given by a smooth function, divergence free, and then you close with respect to this Q topology. And here it is, something I want to point out. This space LQ solenoidal component in which you eventually you're going to work, you want to work on the solenoidal component, is LQ divergence free, and there's a condition on the boundary which is intrinsic in the space, which is G, the element is orthogonal to the normal, so it's tangential. Okay. Instead, GQ is usual, is anything which is the gradient of some function P of suitable regularity. Okay. So for P equal 2, this is about orthogonal projection, but not for P equal different from 2. And here's the story. This is very important to notice. Namely, look at this, the real interpolation space between the solenoidal component of the space and the domain of the linear part of the generator, the linearized part, the generator, according to the indices. For indices, let me start with the favorable situation. For indices which are given in this last line, so for instance, P trapped between 1 to Q over 2Q minus 1, which means what? For D equal 3 becomes 6 over 5. So there's a very small gap here. And for D equal 2 becomes 4 minus 3. So it's also small, but it's even smaller. Okay. So for this situation, you call this interpolation space with the tilde, and what it has the boundary component here, G, which is exactly the one which was part of the space. So this is not an extra condition. It's just being part of the space. Instead, if you go outside this limitation, this small gap involving the P, if you go for the complementary situation, you have a space which is this Besov spaces, which has an additional component, an additional boundary requirement. Okay, so this will impose a compatibility condition. We don't want compatibility condition, so we cannot work with this. We have to work with this because this component here on the boundary is just intrinsic in the property of the space that we are working it. Okay, so the conclusion is that we don't want this situation on the first line because there's a compatibility condition, which is exactly the reason why we could not do the problem of the Navier-Stokes for dimension 3, but we work instead with this subspace of this Besov space, which we put a tilde. Okay, so that's the now. And the theorem is the following. Oh, there's something here that I have to. Okay, what is the unique continuation property, which, as I said, is the starting point of the analysis? If you cannot stabilize the finite dimensional unstable, you just change job because you cannot do anything. You have to start by being able to stabilize the finite dimensional unstable component of the problem. And what do you need? You need a unique continuation property, which is given. We have this paper, we have 4 or 5 or 6 per unique continuation theorem, some for the original, some for the adjoint. Eventually you want for the adjoint for the stabilization. But let me give you some feeling. So you start with a couple, phi and psi. Phi, the L sub B is written in the next transparency, is the Gaussian operator, so it's a linearized portion of the linear component, so it's a Laplacian, and the price you pay, you have an extra linear component which is of order 1, and so you have phi here and pi. So this is a linearized Navier-Stokes coupled with psi, and psi in terms is the linearized the non-thermal equation, which is given here. Is given here, but is coupled with phi. So psi is coupled with phi, and phi is coupled with psi. But psi accompanies this operator ed, which, as I said, in the 3 dimension is 0, 0, 1. So is the unit vector in the z direction. Of course, they have dimension 3. What is the overdetermination? Overdetermination for the problem which I just mentioned, where the control acts, both controls act on an arbitrary small portion of the interior. The overdetermination is that this potential, without this condition, this is the potentially is an eigenproblem. When you put an overdetermination, namely that this phi and psi, this solution here, are 0 on on this arbitrary small portion of the omega. Okay, this is the overdetermination. Then you want to see whether or not the final this is enough, being 0 on an arbitrary small portion of the interior, allows you to conclude that in fact the thing are going to be 0 on the entire omega. And so this is, and I remark is that I don't care about what happens on the boundary. So this gives you an idea. This type of problem you solve with Karaman estimate on the Laplacian. It's a very complicated proof, which I have in the second part. So here you have T3, but there's no time, obviously. I will stop around 40. So this is the proof. I use a Karaman type estimate as is given in this paper, in AMO, etc., etc. Okay. Now, the required problem, however, the required unique continuation is not for the original, but it is for the adjoint. And for the adjoint, you see the theta and the phi change space. Here, gradient of theta is on the first equation, and ED is on the second. Instead, in the thing before, ED was on the first, a gradient of theta sub B is on the second. They switch because of you pass to the adjoint. And so the problem, the one which is required for the solution is to start with, so here you get the adjoint of the Gaussian operator, and you look at this problem up to here, which looks like an eigenvalue problem for the adjoint system. And now the overdetermination is that the psi, the component of the thermal part, static thermal part, is 0 on this omega, but only the first d minus 1 component of phi is 0 on this. So you don't need all of them. Why? Because the psi is 0 on here. So this is 0, this is 0, this is 0. But E is 0 everywhere except the last component. So the d component of phi is automatically 0 from here. So all you need is really to assume only d minus 1. What you want to do, you want to conclude that this overdetermination is sufficient to imply that the solution, in fact, is identically 0. So this gives you the way of checking the Kalman controllability condition in finite dimension. Okay. Now, so the result are local well-posedness and stabilization. The local well-posedness is here. For dimension d equal 3, you start with this gap, which is very tight, this index between 1 and 6/5. For Q equal to is between 1 and 4/3. And then you consider the initial, let the equilibrium solution be given stable. By definition, we want the problem to be stable, obviously, to be stable equilibrium solution for the steady state problem. And then for rho positive, you look initial condition in this space Besov cross Besov. So Besov for the fluid, Besov for the thermal, which satisfy the fact that this initial condition y0 and theta 0 differ from the equilibrium solution in the normal these Besov spaces less than rho. And for rho positive, the result is local. So if rho is sufficiently small, then here it is. For each initial condition in this space of low regularity with these Besov spaces or with these indices described here, then there exists an interior finite dimensional feedback control. Feedback means the U, which was the control for the Navier-Stokes localized, and V, the control for the thermal localized, is given in the feedback form with respect to the solution. So it's something related to Y, the solution, minus Y equilibrium, or theta minus theta equilibrium. And explicitly can be given by this form. So this is a part of the theorem. Is given a finite dimensional. I will say what K is in a moment. So all we have to do, what the proof does, compute, in fact, constructs this vector UK localized in this PK. This is the duality pairing with respect to little omega, and in the feedback form. So when you put them in the, so K is the best you can hope for, namely, is the maximum of the geometric multiplicity of the distinct eigenvalues which are unstable. And because of the issue of the fact that we take the dual rather than the original, we don't need all three components. We need only two in three-dimensional. Okay, so this is only D minus one component. The only constraint being that the last component is always needed, but the other D minus two can be anything we want. For instance, for D equal to, the U may be used invoking only the component, the second component. There's no need for the first component. For D equal 3, you need always you need a third component, but then you need only 1 and 3 or 2 and 3. Okay, so there are only 2 instead of 3. And so what happens therefore, if you put this feedback in the linearized component, in the linearized function here, so this is the operator. So this is nonlinear part. This is nonlinearity of the Navier-Stokes. Okay, and this now the control U and the control V, this for the Navier-Stokes and this for the thermal, which were localized because M is a characteristic function, are localized, are given in feedback form. And then the result is that for this thing here, this is the nonlinearity, this is the full Navier-Stokes written in the feedback form. With the initial condition in this Besov cross Besov as a unique nonlinear semigroup solution in this space, continuously in time with values up to infinity, with values in this Besov cross Besov. So this is a well-posed problem. And the uniform stabilization is here. Moreover, perhaps by taking a rho further smaller, such solution exponentially stabilizing the equilibrium solution in the sense in this space Besov cross Besov, which is as we know, we said before, is a subspace of Besov. So namely, there exists a constant gamma tilde and a constant m gamma tilde greater than 1, such that the solution of this closed loop feedback system, like the thermostat, the difference with respect to the equilibrium solution for Y and the equilibrium solution, so this for the fluid and this for the thermal, in this Besov topology, decays exponentially with respect to the initial condition. So this is a local stabilization problem. Now, the second part I want to do quickly is the fact in which the the control now, there's one component, V, which is scalar, which acts on the boundary of the thermal. Now is the boundary. And the U, which is the interior control, also localized, acts on the Navier-Stokes. So this gamma tilde is arbitrarily small. So this little omega is arbitrarily small, supported by gamma tilde. So this is the support of the control acting interior control localized, the arbitrary small support in the Navier-Stokes. And this is in fact on the boundary. And let me say very quickly the procedure. So namely, the first thing you do in this problem goes back to the Navier-Stokes. You translate the problem by the equilibrium solution component. So you take y minus equilibrium y sub b, h stands for heat, theta is the temperature minus the temperature equilibrium, and the same thing for the pressure. When you translate this problem in the new variables z, h, and chi, what you get this problem here. What do you gain and what do you lose? You gain that there's no more the f and the g, so the forcing terms disappear, and the price you pay is that the Navier-Stokes is now augmented by this component here, which is the Eocene perturbation. You see, y here, the equilibrium solution is known in advance, is the unstable. So this is a first order operator, has this precisely this structure, is first order due to this term here. And so this perturbs the Laplacian and the nonlinearity here. So you have a component, a control on the interior and a control on the boundary, arbitrarily small supported. And then you introduce the various operator to define the abstract version of these things. I will not go to the details, but except for this operator, since the V is on the boundary, you want to go from the boundary to the interior. So you have to introduce some sort of Dirichlet map, which give me something on the boundary, produces the solution, given something on the boundary, the D produces a psi, which is a solution at the interior. And the D is, by elliptic theory, is this regularity. It was very important, is contained in the domain of fractional power of this operator, which is related to the thermal equation. So the equation abstractly can be written in two ways. On the top here, since we have things on the boundary, I have to write in this way if I took the operator on the thermal operator in the original space, because the D does not go in the domain of this B, which is the thermal. So I have to, instead, the difference of the two goes into this domain. If I want to move H over here, like I'm doing in the second part here, so B is being transferred from here to here with the H, then I have to extend this operator here, the extension, because the extension by isomorphism to duality. So the space becomes now D B star dual, because otherwise D does not go in the domain of the BQ. Okay, so this is some technicality which occurs all the time. And then you do the PD form, and this is the operator, the linear part, you see, with the control on the interior and on the boundary. So this is the localized. And I already mentioned this set in the topological setting. So here's the maxima. The maximum regularity is that, so first you show that this linear operator generates a strongly continuous analytic semigroup only the space, which are the space of cross Besov. But this is not enough because the Q is different from 2. You have to show in addition the possessive DLP maxima regularity on it, let's say on the sub Besov cross Besov on finite interval, which is given here. And okay, let me give you the theorem about the well-posedness. So under this is linearized problem, the control on the boundary is written in a feedback form with respect to the interior. So this is the solution. And so V is a feedback of the interior, and is given, you have to construct this function. This is on the boundary because V is on the boundary. So V is a function on the boundary in a suitable subspace, which is regularity. So you have to construct this vector on the boundary and supported on this small little gamma tilde and vector in the interior. And the same thing for W, which is in the solution of the fluid, is given in a feedback form with the same K, which is the best of the minimal possible, namely the maximal geometric multiplicity of the unstable eigenvalues. And so you have to construct these vectors. The proof is constructed. And by doing this, by writing the linearized form in the feedback form, so this is feedback form, so this is the U and this is the V in the feedback form, then turn out that, first of all, this operator, the big operator here, which describes the feedback form, generate a strongly continuous analytic semigroup in the space Besov. And moreover, such semigroup is uniformly stable, given by this in this topology, Besov. So with the control gamma tilde, which is as close as you wish, minus gamma 0 is as close as you wish to the first stable eigenvalue. In addition, this operator is maximal P regularity up to T equal infinity because we have uniform stabilization here. And that's very important for the nonlinear part. The nonlinear part uses in a very strategic way, like in the Navier-Stokes, the fact that this is maximal regularity. And so you get, then for the nonlinear problem, you get the local well-posedness, and then finally, let me write here for the, here the unique, here's the unique, this is the well-posedness, local well-posedness, namely the linearized problem after translation is given in a feedback form in this way here, Z here, Z is here. But you can say that as maximal regularity, and using the trace theorem for maximal regularity, you say that behaves this Z and H, the solution are in these spaces here, very strange. This is the domain of the feedback, but this is embedded in C infinity, C0 infinity with the Besov. And so essentially optimal what you want to do. And the local stabilization is that this linearized here, which have been translated, decays exponentially with respect to this Besov nonlinearity. And therefore, since this is translation, this the original one decays exponentially with respect to the unstable eigenbase or eigenpair, which was the object of the result. Okay. Now, what I want to do next, we want to do now boundary, and later on, so boundary for both of them, and then later on, if time allows, to do also the MHT equation. And I will stop here because the next thing, which I don't want to do, because I'm really out of the thing here, I'm spending 50 minutes so far, is about unique continuation property, which are very, very complicated, but I already mentioned that they're very critical and they require, Kahneman type of estimate, which we had in problem. Then I started with the Navier-Stokes in 2015. Is a very, very complicated proof and requires this Kahneman estimate. So this gives you an idea about the stabilization of fluid, which are given by a composition of Navier-Stokes and thermal in a space, in a setting space. Why did we choose a Besov space? Because eventually we want to do boundary. And to do boundary for the Navier-Stokes, you must have Besov. So that's why we want to train, to check the solution step by step in such a way to go to the, more and more challenging. And the final thing will be boundary for the Navier-Stokes and also for the thermal equation. And I think I'll stop here. Thank you very much.
Well, thank you, Professor Triggiani. It was a very, very excellent talk. Now we have some time for questions. Anyone can open your microphone or write something on the chat.
I don't know how to use things. I think I can answer. I don't know how to do. Jose is here to help me, perhaps, but I don't know how to do the chat story. Ask me the question first, okay?
Okay. Is there anyone to ask questions?
Yeah, please ask question.
Is there anyone?
Yeah, if I hear some question, I will try to answer in because I don't know how this chat, how this used. I'm not technologically, I'm still in 1520.
Okay.
I have a question.
Yeah, sure.
Is possible to solve the problem with the BU control without the geometric condition of figure 1?
I did not use a geometric condition here, except for the fact there was, the support arbitrarily small. They're not geometrical. You're talking about the geometrical condition arising in hyperbolic equation. No, they don't enter here. Okay. The only thing about the geometry, the omega can be arbitrary, and then I take an arbitrary small portion of the boundary. Okay, anything you want. And if I do interior, I can take an arbitrary small interior little omega, but there are no geometrical conditions here.
Yes. Yes.
Now, since I've experienced starting many years ago with hyperbolic, and there is an issue when you take a multipliers, then there are geometrical conditions, particularly in the case of Neumann boundary condition. But this is a different story. So there are no geometrical conditions here. Okay.
Okay. Yeah.
It's smallness. But the boundary can be anything. Can be anything.
Yes. Other question. This model Smagoriski-Boussinesq, then integral o Loran, ¿tienen cómo colocar no chat? Yes.
Okay, now for professor, I have to speak. He prefers.
Sure.
Okay, the question from Juan is the following: about the Smagoriski-Boussinesq model, which is Navier-Stokes equation, with the integral over omega of the state gradient squared.
Okay, so let me go back. Let me go back to this.
Okay.
Yeah, here it is. Okay. Now let me start with the here it is. Okay.
Okay. So the question is the following: about the Smagoriski-Boussinesq model, which is Navier-Stokes equation with the integral over omega of the state gradient square multiplied by Laplacian operator, and the differential equations remain the same. Do you think it is possible to obtain these results?
Okay, so you're saying to modify this by adding an integral term.
Yes, adding an integral term.
Yeah,
Exactly.
I will have to see. I will have to
Multiplying.
see. You see, if you send me the equation specifically, then I can say, because there have to be lower term, non-lower term. Otherwise, what is the coupling here? So the coupling is here and is here, and the issue here is not much for the coupling, by the way, because the coupling is a good coupling. Look, this is just theta, and this is just y. The issue is not the coupling here. In terms of toughness or high level coupling, that's not the issue. The issue is a different sort here. Okay, so if I have a system which is in addition as an integral term, I will have to see how this term is and where does apply to answer the question whether this can be extended or not extended. I don't know.
Thank you, Professor. Thank you.
Well, any more questions?
So just a comment, Robert.
Sure.
Since we are working with the low order ints for the Besov space, so it's allowed to have the strong trace for, I mean, you have strong trace. I mean, the first one usually strong trace, and then the other one.
Yeah. Okay. So here there's no issue with the traces. I mean, the traces do not count into the assumption. The important thing is that the omega and the gamma has to be related to each other. I cannot put an omega here and the gamma here, and then the Navier-Stokes acting here and the thermal acting here. No, they have to be coupled. But there's no issue of traces like in hyperbolic equations.
Okay.
Where the traces behave better than what is suspected when you deduce from the interior. Here is not an issue of the traces. The issue is somewhere else.
Okay.
Because these are parabolic problems, you see. They're both parabolic problems. And so there's no issue regarding the regularity of the traces, etc. Because if you look at also what you want to do, you want to do the solution, namely in the interior, to be decaying. First of all, to be well posed, and then to be decaying, okay, exponentially. So there's not an issue of traces here. It's not like in hyperbolic, okay? When you couple two things and the traces of the hyperbolic, or even for instance, if you couple a parabolic equation with the hyperbolic equation, like in fluid structure interaction, then there's an issue of the traces.
Yeah, the normal trace, the normal trace.
Yeah, there is a mismatch between the parabolic component and the hyperbolic component. Okay, then yes, then use different techniques. For instance, you go back to our techniques back of the of hyperbolic of the 80s, when the traces behave, both Dirichlet or Neumann traces behave, have a special behavior which is better than the regularity that you can take formally by the interior. There is essentially 1/2 more regularity of the traces that you can guess that you can take from the interior. But that's when they have a coupling which is parabolic hyperbolic. Here the coupling is hyperbolic, is parabolic.
Parabolic.
Yeah.
Yeah.
So it's a question that, frankly, who did, as far as I'm concerned, it was Boudica actually that after we did the Navier-Stokes says, oh, by the way, there is a very important, model in the literature which is called in the literature is called Boussinesq. There's an adjective that they use because Boussinesq means also something else. If you talk to people on hyperbolic, Boussinesq means something else for them. Here instead they call Boussinesq blah blah blah. I forgot what it was. There is an adjective which is attached to Boussinesq, but now these are both parabolic. So there's no issue with the traces, see, like in the fluid structure interaction.
Thank you. Thank you.
Sure.
Oh, thank you, Vladimir. There are any more questions?
Can I tell you an example where this Kalman does not work? And then we finish here. Let's start with something, end with something negative, okay? Okay, now, suppose I do the dimension even 2. This unique continuation, suppose I want to do the Navier-Stokes now, not the Boussinesq, just the Navier-Stokes, okay? And I want to do with the control on a small portion of the boundary. I have the Boussinesq, I have a Navier-Stokes, so I don't have this omega, I only have gamma. And I want to do control on an arbitrary small portion of the boundary, and perhaps even tangential if I can, okay? Then the question becomes that you have this unique continuation question for the Navier-Stokes with overdetermination, namely Dirichlet and Neumann boundary condition on a small thing on the boundary. And then you want to ask the question whether this implies 0. Well, the answer is no. If you take an arbitrary small portion of the boundary, the answer is no, because there is an old theorem of Fabre and Lebeau, which actually is done in the 2-dimensional half space. And it's a very simple counterexample. They show that in this half space, even without the Boussinesq system, just Stokes, the answer is very simple to construct. They have it in a paper of 96 or something. Now, from the half space, you go to an arbitrary small when you go from a half space to a bounded domain. Okay, so that's an example in which this Kalman, this stabilization, the finite dimensional, using by necessity using the Kalman condition, does not work. It's not possible to find this F. Okay, so you need to have only think here for the Navier-Stokes is not enough. You need a little bit. So that's another topic. But that's an example in which what I was saying at the beginning, if F exists, okay, it may exist or may not. And when it exists, by the way, it's not easy to show that it does exist. The proof is subtle, and it has to do with the property of the traces or this sub portion of the eigenfunction, either on arbitrary small portion of the interior or else on the boundary. And this was a problem that was not studied by many. I wrote some papers myself, but there's still some open question, by the way. Okay, so this ends with the negative statement, so to speak, at least for the Navier-Stokes.
Okay. Well, there is any more questions? Well, if there if we don't have any more questions, let's thank Professor Roberto Triggiani again for your
Yeah,
very
thank you,
excellent talk.
all of you. I see you in
Thank you.
Brazil. I see you in Brazil very soon. Eh?
Okay.
Oh,
Yeah.
great, great.
Unless the
We're
world
looking forward.
unless the
We're
world
looking
will
forward.
collapse, which seems to be very close to it. Okay.
Okay.
Bye bye to all of
Thank
you.
you.
Bye bye. Bye
Thank you,
bye.
Lorana,
Bye-bye.
and thank you a
Yeah,
lot,
thank you all
Professor.
of you. Thank you. Thank
Thank
you.
you.
Thank you a lot, Professor
Vladimir.
Roberto Triggiani, for
Yeah,
your
we meet
amazing
in
talk.
Bye, Roberto.
we meet